Okay, so we just finished the first half of this proof, where we, discussed that we came to this conclusion right here that the row rank is less than or equal to the column rank. So the row rank of A is less than or equal to the column rank of A. And now the second half of this proof, right? So number 2, we're going to show that the column rank, I can write that better, of A is less than or equal to the row rank of A. Right, and by doing so, by first deducing that the row rank of A is less than or equal to its column rank, and then by finding out that the column rank is less than or equal to its row rank, you eventually come to the conclusion that the row rank must be equal to the column rank. Because if you write out that inequality of row rank less than or equal to column rank less than or equal to row rank, the only way is that equality is even possible is if the row rank is equal to the column rank. So let's go about doing this. So the proof is pretty analogous, right? Like it's flipped on its head. Let V be equal to the row rank. I'm going to write it like this. The row rank of A. And we're going to let D, okay, be equal to a basis for the row rank, for the rows. Sorry. That's going to be D1, DV, right? There's D of them. There's V of them, sorry. And so D, right? D is a set of 1 by L row vectors, right? Because these row vectors, they essentially, these row vectors, right? Imagine these row vectors. Linear combinations of them, right, is going to produce another row vector. And we're saying that the space spanned by the rows of A, all the row vectors that are created by all the linear combinations of A's rows, the basis for that space is a set of basis vectors, which are row vectors. So hopefully that makes sense. And so we can say that D is equal to a V by L matrix of row vectors, which are a basis for the row space of A. So we can say that each row of A is a linear combination of this basis D, and likewise in the other one, we can collect coefficients into a matrix. I'm going to call it E, which is a K by V matrix, such that A is equal to E times D, right? Because A is a K by L, and then E is a K by V, and D is a V by L. And so that the dimensions match up. And then we can say that the columns of E of ED, sorry, are linear combinations, we're shorthanded, of E with coefficients, okay, from D, right? Where, ED, we can pretty much just say A, right? And so with that being said, there are V columns in E. And if they are linearly independent, then their span, okay, is equal to V, right? So A is a linear combination of all the columns of E and D. There's V columns in E, right? And so their span can be at most V. That should make sense. So it's otherwise, right, it's less than or equal to V. And so since A is a linear combination of E columns, right, and E columns, I can do better than that, I'm starting to get a little sloppy, E columns rank, okay, is less than or equal to V, then this means that A's column rank, all right, is less than or equal to V, while we just stated up here that V was its row rank. And so in this case, right, the column rank is less than or equal to the row rank. And so now we've pretty much came to the end of it, right? So now we've pretty much stated, after all of that, we found in the first part that the row rank is less than or equal to the column rank. And then in the second part, we found that the column rank is less than or equal to the row rank. And so if the row rank is less than or equal to the column rank, which is less than or equal to the row rank, then this must mean that the row rank is equal to the column rank. And that pretty much completes the proof. You can look at this inequality and say to yourself, like, okay, like let's imagine that the row rank was 1 and the column rank was 2, right? Well, would this even make sense? Could this inequality even make sense? And it wouldn't, because if you had 1 right here, if this was 1 and this was 2, 1 is less than 2, which is also less than or equal to 1, and this right here doesn't hold. And so the only way that this works is if all of these are the same value, or all of these are 2, right? It's the only way that this works. And so that completes the proof.